Hello, everyone. This is College Algebra at College of the Sequoias in California. This is spring 2020 during COVID-19 lockdown. We're generating a bunch of video files for this semester and future semesters to use as a resource. Hope you guys are enjoying the Professor channel so far. We're getting near the end. This is in chapter 10, and we are still in conic sections. And this section focuses on the ellipse. So first off, the full terminology. An ellipse is the set of points, set of all points in a plane where the sum of the distances from two fixed points is constant. It's unchanging. The fixed points are called foci, and that's plural of the word focus. So ellipses have two focus points. And the equations are almost identical to circles. Let's talk about circles for a second, just as a quick reminder. We had for a circle, x squared plus y squared equals r squared. If we divide both sides by r squared, we get this. Here, these two are equal. The only difference on an ellipse we get x squared over a squared plus y squared over b squared equals 1, and a does not equal b. This generates two focus points, or two foci. The circle only has one. They end up overlapping. And I'll show you that. I'll show you on Desmos. It's really neat watching it happen. You'll notice this is from our book. The lecture notes in the book like to specify whether or not the B is under X or under Y. I think that's foolish. I think it's confusing. I'm going to keep it constant. I'm going to use x squared over a squared plus y squared over b squared equals 1. Let's go into the picture of what's going on. It's not that it's foolish, it's confusing. And I don't really think that it helps stuff later on. So we have two options. So in both cases, we have x squared over a squared plus y squared over b squared equals 1. Option A is greater than B. Option B, A is less than B. So let's explore those. The ellipse ends up being elongated this way. It's an oval, like this. We have a center that goes right through the middle. The vertices are right there and there. This distance here is called B. This distance there is A. Okay? Whichever one is longer, A or B, that leads to that axis ends up being called the major axis. Okay? And the foci appear on the inside. The idea of it being equally distant, let me redraw this. And assuming I had a good picture, this looks like Big Hero 6. So the idea here is we can pick any point on this thing right here, connect the first focus point to it, the second focus point to it. Let's call this A1, or not A1, C1 and C2. Nope, D1 and D2. And we can pick a different point that's, hell, we can do it way over here. Call this D3 and this D4. And it doesn't matter where I do this, D1 plus D2 equals D3 plus D4. It's some fixed constant value. Okay? The reason why I didn't want to use C is we end up using that to describe the focus, where the focuses are located. Okay? In this picture here, C is that distance. C is that distance. In all cases, C squared equals the absolute value of A squared minus B squared. You'll notice that looks a little bit different than what they have here. They do A squared minus B squared or B squared minus A squared. If you just make it the absolute value of A squared minus B squared, we don't have to change the letters around and everything looks great. Not having to change the letters around is much better. Okay? So if you see them use it in the book, know that that's what they're doing. So that was called the major axis. I didn't point out the other one. This other one, guess what that axis is called? If the long one's the major, the short one's the minor. You'll notice the major axis has a length of twice the letter. Length equals 2a here. And here, length equals 2b. The horizontal axis will always be this, the way we keep it. And the vertical axis will always have a length 2b. Whether we call it major or not, just depends on whichever's longer. The longer axis is the major axis. So notice I said in A is bigger than B. So this A is bigger than this B. It's longer here, shorter here. In option B, that changes. A is shorter than B. So let's take a look at that. So option B, the foci are always on the major axis. So major axis, foci are always on the major axis. Their distance from the center is C. Right now, this length is B. That length is A. Notice that A is less than B. So the major axis is our B one. The minor axis is X, or A. The same idea remains the same. The fixed points are the same. You are all very, very aware of an ellipse. It is probably the most important thing in your life, and you may not even be aware of it. Our solar system is an ellipse, and we'll actually explore that later on. And we'll see just how close the foci are to the center. The sun is one of the focal points. And no, Earth is not the other. That'd be awesome. Then we could really say the solar system revolves around us. So when we have our sun, I think I made that really too elliptical, making it look like that way. If this is our center, you're going to see that the sun is really close. That's like our second focal point. There's another focal point over here. Okay. The standard form is, let's look at the generic. I'll write the full form of the equation right now, because I think maybe beating around the bush is not a good thing. We've seen enough of this already. Guess what happens when I do this? Any ideas? This puts our center at HK. Okay? If they are absent, the center is the origin. And when you go down deep enough into math, you'll find that we often like to make the center the origin. And it just has to do with picking up the map and moving it, recentering the map. We do that all the time with a map. Well, on your phone, when you're driving somewhere, the Google Maps automatically recalibrate all the time to keep you at the center of the map. It's the same concept. So we've got x squared plus, we've got this form here. So the foci in this form. So let's look at option A. That was where A was bigger than B. The major axis is horizontal. has the focal points. Recall c squared, I told you, was absolute value of a squared minus b squared. The foci are at h plus or minus c comma k. If the center is the origin, plus or minus c comma 0. Option B, A was less than B, the major axis is vertical, and has the focal points. Again, c squared is the absolute value of a squared minus b squared. Obviously, we need to take the square root. The foci shift to being added to the k. Foci switch over to being h k plus or minus c. We'll explore this at the origin, and then we'll dive into the full version. But I thought showing you the full version is a good way to start because it doesn't change much. Just adding that center doesn't really do a lot. The vertices for these, maybe I should list them. We add a or subtract a from h. And the vertices here, we do the same thing on k, but it's with b. Okay, ready to look at some examples? So example 1, let's find the foci and graph the equation. And we'll start off it in a form that is not traditional. When you see an x squared and a y squared, indicate a round object. Maybe a circle, maybe an ellipse. In either case, it doesn't hurt to make the right side equal 1. The constant side, let me say that. If you have all the variables on the right, it doesn't make sense to make that equal 1. Make the constant side equal 1 by division. So what I'm going to do here is I'm going to divide everything by 100 because that's what's on the right. Hundred factors. 100 is 4 times 25. And that's going to let me cancel out some stuff on both sides. Bring down my equal sign. 100 divided by 100 is 1. I can cancel my 4's out now, and I get x squared over 25. And I get y squared, the 25's cancel, over 4. This is the same form as x squared over a squared plus y squared over b squared equals 1, which means we can pull a and b directly from the equation. A squared equals 25, a equals 5, b squared equals 4, b equals 2. So I'm going to graph it, and then I'll find the foci. My center is 0, 0, because I had nothing in parentheses with the x and the y. To graph the ellipse, all we do is we go a units left and right from the center. So that's a equals 5 this way, a equals 5 that way, 2 up, 2 down, b equals 2 in either direction. And we connect them in a nice little arc. Try to make it look round. It's not a diamond. My vertices are the endpoints on the major axis. -5, 0, and 5, 0. I need to find the foci, which means I need to find C. What is C? C squared is the absolute value of a squared minus b squared, which is, since a squared is bigger than b squared, I don't need the absolute values anymore. 25 minus 4 is 21. We take the square root. C is the square root of 21, and that's approximately 4.6. The focal points are exactly C units away from the center. This is 4, this is 4.6, and we'll have -4.6. So that's a focal point, that's a focal point, and we've got -4 point, probably better off keeping accurate, negative square root of 21, 0, square root of 21, 0. That's probably the best choice. Only do this to graph. Okay? In the real world, as soon as you do that and you round to 1 decimal place, you have lost a lot of information, and it might be just enough to sink or swim the next thing. Okay? Not too bad. Let's keep going. Oh, let's look at this one in Desmos. Actually, let me put that back out there. So we had a equals 5, b equals 2. I have it set up to show focal points no matter where they're at. It's always the ones inside the ellipse, but it's a little hard to tell Desmos. Use whichever ones works better. This inequality portion right here is what's giving it the shading. That's kind of neat. We say equals is now just the circle or the ellipse. If I say less than or equal, it shades inside. If I just do less than, it shades inside but puts a dash on the edge to show don't include the edge. I think it's a little bit easier to see everything when you got it like that though. And C, I said was approximately 4.6. I have it set up as a calculator right here. That's this right here. This is called eccentricity, and I'll talk about it in a little bit. I have that set up, but I've got the labels. There we go. So it's showing what we have, okay? All right, let's take a look at our next problem. Our next problem, I'd like you to give it a try first. See what you come up with. We've walked through how to do one of them. See if you can extrapolate what to do here. All right. What's the first thing we wanted to do? You want to make the right side equal to 1. Let's divide everything by 441. Now, what you should do every time you see something like this, check to see if 40, like these two numbers here, multiply to make that number over here. Because if they do, everything cancels out just fine. 49 times 9 is 441. Which means I can replace that with 49 times 9. And I can replace that with 49 times 9. And then just cancel what I need. This equation here, the 49s cancel. I'm left with x squared over 9. Oh, sorry. Earthquake. The y terms, the 9s cancel. I'm left with y squared over 49, and the right side's 1. What does A equal here and B equal here? Well, I know A squared is 9, B squared is 49. This tells me A equals 3, B equals 7. We always needed the C's. C squared is the absolute value of A squared minus B squared. Absolute value of 9 minus 49 is the absolute value of negative 40, which is 40. So C equals the square root of 40, or 2 root 10. And we'll see that's approximately 6.3 for graphing purposes. Where is our center? There's nothing in parentheses with the x and y, so our center is at the origin. A is short, B is long. This is going to be a tall ellipse, not a wide ellipse. So I need to go 3 in either direction this way, 7 in either direction this way, always make sure that it's rounded. The shape. This is not a diamond. It amazes me how many students are lazy and just start drawing straight lines, make a diamond out of it. Just practice doing curves. It's not hard. Your shape may look ugly. This isn't a perfect ellipse, but it looks round. It looks like an egg, right? It looks eggish. Which of these are my vertices? The vertices are always on the major axis. The major axis is the long axis. So that point is a vertice or vertex, and that point's a vertex. 6.3 is relatively close to those, and it's on the major axis. So that's a focal point. That's a focal point. And my foci are at 0 plus or minus the square root of 40. Or 0 plus or minus 2 root 10. That's probably the cleanest form. As soon as you point 6.3 in, you start losing some info, and I don't recommend it. All right, the show must go on. Let's do some more. Oh, wait. We got Desmos. Let's explore it. So we've got A equals 3, B equals 7. And we said the foci were at about 6.3. That looks right. It's going 3y. I'm going to take those labels off. Those are distracting. We can see the points. They're big black points. You put your cursor over it, it tells you where it's at, or you click on it. We can see it goes to -3 to 3, from -7 up to 7, just like our graph does. Okay. And notice I haven't had to change anything in here. By keeping A with X and B with Y, all you have to do is change the parameters in Desmos and everything else updates. And it's easy to remember that A goes with X and B goes with Y. That funny mumbo jumbo stuff they have right here where we're going to change what letter goes with what. On the horizontal one, A was with X, B was with Y. The vertical one, they switch it. They change the equation for C squared on both of them. That's just confusing. I think if you give this a try, you'll find this works better for you. So let's kick it up a notch. Now, we're not going to start with the equation. Find the equation of an ellipse centered at the origin with foci at plus or minus 5, 0, and a major axis that is 18 units long. Okay. So let's just draw what we got here. Maybe drawing a picture will help. My foci are here. Which axis is the major axis? The foci being on X tells us this is the major axis. The major axis is 18 units long, which means the entire width needs to be 18 units. We'd split that in two. 9 go that way, 9 go that way. And those are my vertices. Vertex at 9, 0, and vertex at -9, 0. That's a focal point. That's a focal point. What does the 5 give me? What is this number here, first off? The distance from the center is A. So 9 equals A. That seems important. In fact, A, B, and C are all important. A is 9. What does the focus tell us? The foci tell us the distance from the center, and that distance is C. In this case, C is 5. We know A is bigger. Let's see if we can find B. C squared equals A squared minus B squared. A is bigger than B because it's the major axis, so I don't need the absolute values. This will be positive. Let's plug in what we have. 5 squared equals 9 squared minus B squared. $25 equals 81 minus B squared. I'm going to add B squared to both sides and subtract 25 from both sides. That keeps my B squared positive. 81 minus 25 is 56. So that tells me B is the square root of 56. Which is 2 root 14. B is approximately, what is it? What's the square root of 56? Seven 7.5-ish, 7.48. If I want to draw it, the minor axis has 7.5 and 7.5. The major axis is 9 and 9. It's almost a circle. And what's my equation? Which is what we were supposed to find here. We know that x squared over a squared plus y squared over b squared equals 1. When it's centered at the origin like it is. A squared is, 9 squared is 81. B squared is 56, it's right there. In fact, if I wasn't graphing it, I didn't even need to calculate B. See, almost circular. I'm gonna go back to making it a slider. Watch what happens as B gets close to 1. Watch what happens to the focal points. A little bit faster. Well, when A and B are the same, the focal points are overlapping. There's just one. They're at the center, and it makes a perfect circle. As soon as A is a little bit different than B, we start having an ellipse. The further apart they are, the flatter or narrower it looks. Looks pretty narrow. That was neat. That's neat looking. Okay. So I wanted to show you that, how as A and B approach each other, the focal points get near each other. B is negative, which is to make it a trip out. But we can see as B gets closer to A, look at this. We're getting at 2.7, 3, 3.5, 4. As soon as we get to 7, those focal points are coming to the center. We're at 5.5, 5.9, 6. And you can see like even 6.9, they're still pretty close. 6.9, 1, 7. It looks circular, right? You'd have a hard time telling otherwise. All right. Let's go back to another problem. Let's see. So let's graph y over 3 equals negative square root of 1 minus x squared over 4. What would you say we should do first? Any ideas? Maybe square it? That'll get rid of the square root. If I square this side, I get y squared over 9. On this side, negative squared is positive. The square root goes away, and I get 1 minus x squared over 4. I can add the x squared over 4 to the other side. we get x squared over 4 plus y squared over 9 equals 1. So what do A, B, and C equal? What's my center? What's my major axis? A is the square root of 4 is 2. B is the square root of 9, which is 3. C squared is the absolute value of 4 minus 9, which is negative 5. Absolute value of that is positive 5. So C is the square root of 5. And the square root of 5 is how much? Approximately 2.2. My center is where? 0, 0. Which one's the major axis? It should be the vertical one. B is bigger than A. Go ahead and take a second to graph this. While you're graphing it, I'm going to type it into Desmos. And then I'm going to graph the original equation. Okay. There's the whole circle, the whole ellipse, I should say. 3, 3, 2, and 2. Look what happens when I turn that off, though, and I graph the original one. What's the difference? Why does this one have the upper half and this one doesn't? The actual one is the bottom one. What's going on here? This is only half an ellipse. The problem was at the beginning. Y over 3 equals negative square root of 1 minus x squared over 4. What is this saying? Negative of the square root is a negative number. Even if I multiply it by 3, y has to be less than 0. So this ellipse is restricted. Stay on the lookout for sneaky crap like that. How does the inequality symbols change this? Kind of curious what it looks like. Huh? Looks like a lightsaber. Funny. Okay, I'll turn that off. Okay, so what happens if we change this? What if we change it to x minus h and y minus k? Let's take a look at some of those. The focus, notice how the foci aren't in it anymore. We got to change this to h plus c, h minus c, k plus c, and k minus c. Why does that look funny? Something's off. What is off here? Let's change these values. Make these 0 real quick. That works. As soon as they're different, something's not right the way I got Desmos set up. So maybe we'll have to ignore Desmos on that portion for a little while. Let's do it by hand. So now we're looking at x minus h squared over a squared plus y minus k squared over b squared equal, or plus, sorry. Oh, did I have that wrong? Oh, neat. Oh, that's what's wrong. Now I got it. There we go. Much better. All is right in the world. All right, that looks better. All right. Now it's getting a little frustrating, right? So as I was saying, our center, well, our foci either end up being h plus or minus c comma k, or h k plus or minus c. This is for major horizontal. And this is for major vertical axis. Okay. So let's look at some examples. X minus 3 squared over 36 plus y squared over 9 equals 1. Let's graph it. Find foci, vertices. Oh, we haven't done this on ellipses yet. Domain and range. So where's my center? Center is HK. In this problem, that is 3, 0. A is the square root of the value under X, 6. B is the square root of the value under the Y term, 3. If we do C squared equals A squared minus B squared, we get 36 minus 9 is 27. So C equals the square root of 27, which is 3 root 3. And if we want to approximate it, it's about 5.2. Now we graph it. That's my center. I'm going to put a dot there. I need my A to go 6 left and right of that. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6 over here. That's my X, that's my Y. From there, I'm going to go B up, B down, B left, B right. My foci are 5.2 away from the center along the major axis. 1, 2, 3, 4, 5, right about here. So there's my F. We'll call it F2. F1's over here. This is V1 and V2, my vertices. What are the values here? This is the origin. 1, 2, 3 left is -3, 0. This was 3, 0, and we go right 6. 1, 2, 3, 4, 5, 6 is 9. 3 plus 6 is 9. The shortcut for the foci is to write HK and then say plus or minus C in it. This is 3 plus or minus the square root of 27, 0. So F1 is 3 minus the square root of 27, 0. F2 is 3 plus the square root of 27, 0. And if we use the 5.2 approximation, 3 minus 5.2 is about negative 2.2. And 3 plus it is about 8.2. Domain and range. Where does our graph start? On going left to right, it starts at negative 3 and ends at 9. Vertically, it starts at negative 3 and ends at 3. That's all that does. That's all it does. We'll change this to match that. A equals 6. B equals 3. What's off here? Those are outside it. These are supposed to be my foci. Did I put the wrong value? H is 3, K is 0. It's not centered at 3 though. Do I have the wrong A in? Oh, I have a 2 up there. There we go. Okay. That's better. Sometimes you got to tinker with these, get the graphs just right. Once you have them, saving them though makes them really fun to play with later on. A lot of learning going on here. All right, so I mentioned this value right here. Let's talk about this right here. What is that? So there's something on circles, ellipses, the conic sections called eccentricity. It's not how eccentric you are, it's measure of roundness. And it goes by the letter E. And it's important to note, this is not the exponential E. That E is always, what is it, 2.8 something? 2.718. There we go. That's the exponential E. So the eccentricity E for parabolas, they say E equals 1. For an ellipse, E is between 0 and 1, but not equal to 0 or 1. And the way I did A and B for an ellipse, E equals C over A or B. And what we put here is put the larger value in. Larger value of A or B. A lot of computer programs allow you to do that with a max command. This says pick which one number is the max, A or B, and use that value. Okay. So for like flat ellipses like that, E equals C over A. But for vertical ellipses, E equals C over B. So ellipses are always like that. Circles have an eccentricity of 0. And hyperbolas, which we'll do in 10.3, E is greater than 1. Why is C equal or E equal to 0 for circles? C squared equals A squared minus B squared. Circles, A equals B, which means C squared equals 0. And it doesn't matter which one's on bottom, E is going to be 0. Okay. So let's take a look at a couple that help. You guys have heard of Halley's Comet. In fact, just last night, I didn't go out because it was late in the night. There was supposed to be meteors from Halley's Comet interacting with crap in the atmosphere, or outer space. So this is Halley's Comet. Let me draw the sun. Or our ellipse is fairly round. Our center is here. The sun is super close. Halley's Comet has an eccentricity of about 0.97. It's doing some stuff like that. That's like Halley's Comet. To put it in comparison, Earth's eccentricity, its orbit around the center, or its roundness of how it goes around the center, is about 0.017. We are almost circular in orbit around the center of our solar system. And the reason why is the sun is so close to the center. Hold on one second. Zoom, fit to page. So we can look at some examples. They're fairly straightforward for eccentricity. X squared over 81 plus y squared over 100 equals 1. All we're going to do is find E. We've already practiced graphing it. So C squared is the absolute value of A squared minus B squared, which is the absolute value of negative 19. So C squared equals 19. C equals the square root of 19. A here is 9. B here is 10. We go with the bigger one. E is C over B here. Square root of 19 over 10. And if you work that out on a calculator, it's approximately 0.436. Let me give you guys one to try. Find E. Okay, I'll assume you paused it and worked on it. So for A, we have the square root of 11. B is the square root of 6. C squared is 11 minus 6, which is 5. So C is the square root of 5. What's the bigger value there between A and B? A is. What is that about? A little over 3. Square root of 9 is 3. So square root of 11 is a little bit higher, maybe 3.3, 3.4, 3.3. Square root of 6 is a little bit above square root of 4, a little bit less than the square root of 9, but it's closer to 4. I'm guessing this is about 2.4. Let's find out. 2.449, yeah. So A is bigger. I'm going to put the square root of C, or C, over A. And if we rationalize that, we multiply top and bottom by square root of 11. This is square root of 55 over 11. That's the accurate one. If you do an approximation, you should get about 0.674. Okay. One more example. This helps show how some of the power of some of this. So, come on, stop that. Let's take a look at Jupiter. This is a critical thinking problem. Jupiter has an eccentricity. It's really eccentric. Not really. Its eccentricity is small as well. Its maximum distance from the sun is 507.4 million miles. Find its closest distance. Now I want to say those are called ahelion and perihelion. Let me look them up. No point in not using some good science lingo while we're doing this. Oh, free points. Perihelion, aphelion. So aphelion is farthest from the sun. Perihelion is when you're closest to the sun. There's some fun science terminology for you. I know you guys know I like NASA. I worked for them for a little while. Big on space and stuff like that. Wanted to be an astronaut. Let's draw a picture of what's going on here. This might help a lot. And that, I know the solar system isn't very oval, but I think making it look more oval than it is helps emphasize what's going on a little bit better. Here's my center. The sun is at one of the focal points. The max distance is going to be along the major axis, which means this distance right here, right? That's my max. The way the shape is drawn, it doesn't look like it. The min should be over here. So the assumption we're making is min is the opposite of the max. We need to do that. Otherwise, if we don't know where it is, this is a hell of a lot bigger of a problem. What's this distance right here? That's A, right? What's that distance right there? The letter we gave it was C. The vertical distance is B. So how long is this distance from here to here, that max distance? Well, it's got to be A plus C. And we just said that's 507.4 million miles. What about this distance right here, the minimum? Well, the full length right here is A. We're losing C. The minimum distance is A minus C. Does that make sense? Okay, so let's use that. Yeah, let's use that to our advantage. So what do we have? A plus C is 507.4. We know the eccentricity. E is given to us, 0.0489. What else do we know about E right here? The way I set it up, E equals C over A. Right? I chose that as my major. I could have done it vertically and used B, but the way I drew it, it's easier on a page to go horizontally. So what does this tell me? 0.0489 equals C over A. And if I multiply both sides by A, I get C equals 0.0489 A. I can take that and plug that in right there. And I get A plus 0.0489 A equals 507.4. We'll leave off the million miles. Let's not forget about it. It needs to go back in later on. Those are our units. So I combine these. I get 1.0489A equals 507.4. Divide by that 104. And you get approximately 483.745, again, million miles. That's not what they asked us though, is it? We want to know A minus C. Well, I have A. This is A. Looks like all I need is C for the min, right? I have an equation for C in terms of A though. times 483.745 million miles. And I get C is about 23.655 million miles. So my minimum distance, 483.745. I use more significant digits than I should. I can trim it down right now. This is about 460.1 million miles. Okay. So our solar system isn't the only thing that this stuff is good for. Other places that show up on ellipses, I'm sure there's racetrack entries that show it really well. I want to tell you about one you may never have heard of. So a real life scenario or a real life example of this. They're called whispering galleries. If the room is built like an ellipse, if we've got two focus points, F1 and F2, any sound made at F1 is easily heard at F2. And vice versa. Just like the parabolas, all light got reflected in the same way. That's what's happening with sound here. Doesn't matter what way the sound goes from the source, it all ricochets towards F2. Some famous places that were built like this, Hall of Senate. In fact, ooh, my camera, there we go. Look this up, it's a fun fact. Ben Franklin's seat was at a focal point and he knew it. He didn't discuss anything at his desk because he knew how sound moved. He just eavesdropped on his opponents. On his political rivals is a good way to say it. Who had a seat at the other focal point. Now, they told me this when I was visiting the Hall of the Senate and stuff like that. I assume it to be true. He's a clever man. He was very clever. He knew a lot about math. You look up magic squares and stuff like that for Ben Franklin. There's some good stuff there. The point is, this is an example where all sound goes from one spot to the other. In fact, if you built an auditorium really well and you knew it was elliptical, you might put a receiver at one and the speaker at the other, like an amplifier. No, that doesn't make sense. We use electronics nowadays. Ignore that. This is an old school use of it, okay? That wraps up 10.2. Pieces, deuces, later.